This is the introduction to kinematic systems. For the first video, let's start with the steering wheel. So yeah, this is the steering wheel. This aluminum plate was water jet cut. That's just like a machine that we have in the machine shop. It's really good for cutting out flat patterns. So anything that you can make flat that doesn't have to be CNC, that's just a really good way to make something. This is also a good example of what critical fasteners look like. These bolts right here don't have any, you can't put a nut on the inside of there. So they have to be tied off. So this is the tie wire, and the way it works is if one nut tries to back itself off, then it'll tighten the other joints.
Okay. And then those two buttons, is that to start the car?
Yeah, so two bottom buttons are to start the car. We also have data flag, radio, and neutral request. And I think the last button is just an extra if we want to program anything later. Yeah, this is the quick release. It goes on right there. And as for the rules, we have to have one of these quick releases so that a driver can move the steering wheel and jump out of the car really fast. Because one of the things we have to do is a driver egress, and that's when you go, like, you're strapped in the car and you've got to jump out of the car and This is a pretty cheap quick release. It's like 50 bucks, and it's an aluminum one, and it's got a hex pattern. And one of the issues is it's got a little bit of slop in it. And so we're thinking of going to a splined quick release, which will have a lot less slop. And also, because we have to spend like 300 bucks on that thing anyway, we may as well just upgrade to pin-out, like internal pins. So that actually has the wires from all the buttons on the switches go through the inside, so you don't have to have a cable down.
And also, depending on how we decide on clutch, that might also be a project.
That's the other thing. So there's paddle shifters here, but then you also might have an electronic clutch. So that when you go into a spin, you want to grab the clutch really quick so you don't stall the engine. And so the clutch might be some sort of rocking system down here that you can get at, like, just with those fingers. So if you're going in a spin, you can just slap it really hard. And if it doesn't matter which side you grab it from, it always engages the clutch, then it'll be good for spinning.
And you only have to clutch in to start in this car, like a motorcycle?
Exactly. So whenever you're not moving, that's when you use the clutch. But for shifting, you can just go up and down the pedal.
It would also be great, Aiden, if you could show the old steering wheel and see how we improved from that.
Where did that? Hey, Kieran, did you see where that Mark II? Oh, here it is. Yeah, so this is Mark II steering wheel. That's this chassis, which we're going to be rebuilding Sunday. And as you can see, it's a lot bigger than the other steering wheel. And even though it's carbon fiber, it's it's just way overbuilt.
But it is by far the most beautiful steering wheel.
It's very pretty.
It's a very pretty steering wheel.
Paddle shifting.
Yeah, exactly. And then those paddle shifters just trigger this electronic solenoid, and it pushes the gear shifter in and out and changes gear. Because we use the stock transmission that's on the motorbike engine, so it just shifts exactly like a motorbike. Cool. Okay. Next, we can move on to the Bevel Box. So the whole steering system is pretty straightforward. Bevel Box is just a set of gears that transfers the rotation of the steering wheel to this shaft. It goes down to the steering rack. Now, the steering rack is just a rack and pinion. It pushes the rods back and forth, and that's what moves the tires. The Bevel Box is a bit up for debate right now because we don't know if we're using the Bevel Box or one of those universal joints. Because the universal joint is a lot lighter, but we just might be limited for packaging here, because if you come around here, a universal joint can only bend your shaft 35 degrees at most. So you have to get this shaft, if it's horizontal, all the way down to here, because you can only move the steering rack so far forward, because it can't be like out here in front of the tires. You know, that geometry is pretty important. Next, let's talk about suspension. So I remember in my first year when I looked at this, it was like, that's just a mess of tubes, and I didn't understand what was going on. But it's actually fairly simple. This is called double wishbone suspension. It looks like two wishbones, so here's one and here's two. There's one on the top and one on the bottom. We also call these AArms because they look like A's. But yeah, essentially, they attach to the chassis here, and then they attach to the uprights there. So this is one hinge point on the upright, and then the lower one has another hinge point. So if you were to draw a line between those two bolts, you would get the kingpin, is what we call it, and that's essentially the line that the wheel rotates around. It's just like the hinge fault.
Yeah.
Yeah, and then so in order to define the plane, because this is essentially just a plane in 3D space, you also have the steering link. I'll talk about this funky thing later, but that's just, yeah, again, pushing the wheel back and forth. And then you also have this, which is a pull rod. And it transfers the vertical motion of the tire to the shocks down here. If you stick the camera in here, you can see that when the wheel is going up, it's pulling this bar outwards, and that's compressing this spring. So if I push on it, you might be able to see that move a little bit. So that is just independent suspension, which means that neither tire is linked together. It's just you have one tire and one shock for that tire. This is a lot different from the system that we're going to move to with Mark IV, which is the roll heave suspension system, which we showed you guys earlier. But that will be a big project that we'll have one of you guys design. The rear roll heave suspension system hasn't been designed at all. The front one is more or less complete. But we still haven't designed any of those bell cranks or any of the mounts for the bell cranks.
I have a question.
Yeah.
So moving forward, what is the material going to be for the A-arms and the pull rods?
Great question. So these ones are steel. Steel A-arms are really easy to make. Another project that we're looking into is carbon fiber A-arms. They're fairly doable. You basically just have to test your inserts. So you have a carbon fiber tube, and then you machine a little insert that you glue into that tube. And that insert is what connects to your joint with this little swivel joint. And then we'll take them to the Kinematics lab at UBCO and pull them apart with that big brake machine that they have and see how much force it takes. But as far as like the car is concerned, that's kind of a low priority because we can go to competition on steel A-arms and they aren't actually that much heavier, but carbon fiber A-arms are cool and they're a little bit lighter, so they're a nice project for stuff. Moving on, we can talk about the rear suspension, which essentially is the same as the front, except there's two differences. One is that the rear tires don't need to move, so rather than having a moving link for the steering rack, you just have a rigid toe link, so this attaches along the same plane as this A-arm, and it doesn't move at all, it just holds the tire straight. Something that's kind of interesting about this is that it matters the geometry that you put this at, because when the tire's moving up and down, you don't want that distance to change, because then the tire will also turn as it's moving up and down. So one strategy is just to have this like on the exact same plane as the bottom A-arm, because then the tire doesn't move back and forth. On the front suspension, you really have to pay attention to that because you can't just put it right in the ring because there's a steering wheel, right? So it has to kind of be up, but there's like a trick you can do where you connect two lines to make sure that you don't get any bumps. Other things to talk about, there's a big axle back here that just drives the wheels. It's connected to, it's called a CV joint, and it basically just looks like there's three prongs with some rubbing inside of those prongs, and it allows the axle to transfer power to the wheel, and it's able to move like in and out and up and down. So at any angle, it'll still transfer power. Yeah, and then all of this is powertrain, but it's just comes back to a differential. That's this guy here, and then that's driven by a big chain. There's a sprocket in here that goes to the. It's kind of hard to see, but if you can get the camera there. Yeah, and then again on the back you can see the rear shocks really clearly. One difference is that the rear uses push rods instead of pull rods. That just basically means that this suspension link is in compression instead of tension, like it is on the front. So when the wheel comes up, it's pushing on, rotating that, and pressing down on the motor. For the rear suspension on Mark IV, when we're going to the roll heel damper system, that has to be mounted like right around here. It'll be really small because it kind of has to be close together. So this bar has to kind of clear this tube and come up around and actually around here. So someone is going to get to design all that, and they're going to have time figuring out all of that geometry and how to mount it, because there's nothing to kind of anywhere near here that you can attach to easily. So that'll be a fun design project.
Will it be the same shocks on the roll view?
Yes. So the shocks we're getting are Multimatic. They're a company that just came out with a set of shocks that are specifically for FSCE teams for roll heat dampers. He worked with them, and we're hoping to get a sponsorship.
They were developed by a student on a co-op there who was on a Formula team. So he designed the dampers and put them on their team's car, and then they went to all the other cars. So, yeah.
Okay, so this is the pedal box. I designed it. I'm not very happy with this design because I designed it to be really easy to maintain and easy to adjust, and it wasn't either of those things. One of the reasons for that is that in order to adjust it, there's like a pin way down in there. And when we go to competition, that pin had to be a critical fastener, which we thought meant it had to be a bolt with a nylock nut on it. In reality, there's like a really fancy quick release pin that McMaster car sells that we can get to make that easier. There's basically like a single rib that runs down the middle of it, and that's what it runs across. And this project right now, Joao has it, but it's kind of a big project, so we'll probably get somebody else to work on, say maybe the gas pedal. Yeah, there's a lot of things that we're going to change about it, particularly the brake system, just because our brake system it took a lot of force for the driver to actually brake the car. We did some calculations with car data and some test data from the track, and it takes 200 pounds from the driver's foot to decelerate the car 1 G, one gravity of deceleration. So our goal this year is to cut that in half. We're going for 100 pounds per G of deceleration. And one of the ways we're going to achieve that is increasing the mechanical advantage of the brake pedal. So if you have, right now the master cylinder is like this. Yeah, if you bring it up a little bit more like that, then you just get more mechanical advantage.
You don't have to push it as much too.
Yeah, exactly. You get more pressure in the brake lines, but we're like, these brake lines are built for road cars. We're not getting anywhere near their yield limit, so that's going to be fine. Yeah, the braking system is kind of straightforward. There's two different master cylinders here, so they put pressure into the two different lines. So our back tires are on one line, and then the front tires are on a separate line. And what that does is it allows us to control the bias between our front brakes and our rear brakes. So when you brake, your weight transfers onto your front tires. And since there's more weight on those front tires, you can brake them harder and get more overall braking force. So there's a little balance bar in here, and that just looks like a pin with a bearing that slides back and forth. And it works exactly like a seesaw with a fulcrum. So if you move that fulcrum over to one side, then it's going to push different amounts on either like the front master cylinder or the rear master cylinder, and that's how we adjust our brake lines. There's also, these are brake fluid reservoirs. And they're kind of just in the way right now. Like, this works, it's fine. You got these flexi hoses that feeds them into the master cylinders. But what I would like to have for next year is smaller brake reservoirs, and also mounted on the brake pedal or the master cylinder. So if you can move these over here, you don't have to have like really big tubes that get in the way with everything, because there's already a bunch of wires. Yeah. And then it all just moves with it when you adjust the pedals back and forth.
One question. So that percentile you said about the height sort of thing.
Yeah.
So is there any way, like, there's like a sweet spot of the pedal box that can be placed so that we won't need adjustable
Not
pedal
really.
box?
No, because you have to accommodate, I think it's like 5'3" to 6'2", and that's like almost a foot difference, so you can't really, you kind of have to have a pedal box adjustment. Another idea that we had was just placing extenders on the foot pads. So like the pedal box is here, but you just have a jack. But that's like kind of janky.
Yeah.
You want to do that?
What about what I was thinking, like fix the pedal box, but we have an adjustable seat or something?
That's possible, but what you got to think about that is that then you're moving the driver, and the driver, other than the engine, is the heaviest thing in your car. So if you're moving that weight around, then you're messing around with the center of gravity of your car. And engineers, we like to keep everything constant, so you want to keep your center of gravity as predictable as you can. You don't want the car to be driving completely different from one driver to the next just because they're a little bit heavier. We already have to deal with that a little bit because the driver's in the front of the car, so the heavier the driver, the more weight is going to go on the front tires, but there's not much you can do about that.
What's the seat made of?
Fiberglass and duct tape, and also foam. So we went in and like stacked a whole bunch of foam layers. You can kind of see them, and then we went and filled in all the cracks with expanding foam. And then the actual fiberglass shell, it was made with Andrew's butt. He actually sat back in like this little shell that we made, and then you put garbage bags behind his back and under his butt, and you fill them with expanding foam, and then they expand up and like conform around your body. You know? So yeah, that's how we made this shell, but then it kind of kicked us in the butt because it ended up being really hard and it's not comfortable for everyone. So we're using a different manufacturing method, which is basically the same thing except not putting a fiberglass shell on it. You just leave it the foam and you sit on top of that with just like a cloth cover or something.
Although this seat looks more janky, can you maybe show the other more beautiful seat?
So this is Mark II. And they actually had time to build the seat, so it looks much better. This is what ours was going to look like before we put the duct tape on it. Yeah, and it's all carbon fiber. You got spots for your harness. We have a 6-point harness, by the way, so there's 2 points that mount like between your legs, and then also obviously 2 points above your shoulder as well. And then when you take this out, it's actually really light. It's a lot lighter than that. You can see like this is the foam plates, and then all the stuff that they filled in with expanding foam. So this is like a hard surface, and it fits nicely in front of the wall. So yeah, we're trying to make this instead of this here. But that's all Aero Team's job. We don't really have to worry about that. What we really have to worry about is the seat harness. In fact, you can see it a lot better in this car. This is one of the seat harness mounting points, and then this is another one. It's basically just an eye bolt that screws into there, and then that's where you hook the hook of your harness.
One question. So you keep on saying the word nylock nuts. Something that I did not know. What is a nylock nut?
This is a nylock nut. So you've got, yeah, sure. So this is a non-nylock nut, and this is a nylock nut. It's called a nylock because it has a little bit of nylon around the inside, and if you try to put a bolt in it, maybe this is the right bolt. Yes, it is. That nylon will grip the bolt, and it won't let it undo. So if I try to put this on, like I won't be able to just finger tighten it all the way on. I'll have to get a wrench, and then you also need a wrench to get it off. Another thing that we're going to try to redesign is the dash here. This is a really good looking dash. It's carbon fiber and it's all blue with our colors. But because it comes down like almost to the steering wheel, when the driver is jumping out of the car as fast as he can for driver egress, a lot of times we're hitting our knees on this, and it's fine, it just lifts up. But we want to redesign this dash panel with much more of a minimalist, so like nothing's in the way down here, and we also want it to be lightweight. So,
what are some of these things for on the dash?
Ooh, good question. This is go mode, that turns the fuel pump on. This is your kill switch, so that's like a master switch for your whole car. If there's a fire or something, or if you're doing driver egress, you slap this and then you jump out. This is an AIM dash. It's a pretty expensive unit. You can get all kinds of readouts with this. And it also integrates with our data recording system. So when the car actually drives around the lap, we have telemetry on it, and you can actually see with GPS its path. And there's like with Race Aim Studios, there's a whole bunch of data analysis. So every single sensor on the car, you can analyze it like for each corner and each turn. It's really cool. So yeah. Another thing that we really want to move for is waterproofing everything. So if you'll talk to electrical, they use a thing called Doge connectors. They look like this. Yeah. So just so that everything's like automotive grade waterproof. And that's something that Kinematics hasn't done the best at. The steering wheel looks fine because it's aluminum, but if you look on these steel paddle shifters, there's a little bit of rust burning for them, just because, like, you know, in a perfect world, we don't want the car to get rained on, but like shit happens, we got rained on at competition, and stuff starts to rust. So anything that you're going to put on the car on Mark IV that is steel, we're going to paint it. That's what we did for things like the AArms. Those are painted black, except for where they're not. And then that just, it's just a rust protection.
Maybe you want to explain the brake lines?
Sure. So the brake lines, they come off the master cylinders. This stuff right here, this is called Flexi line. It's basically just a flexible brake line, and it's much more expensive than the rigid stuff. And then that interfaces with this stuff, which is just like a solid steel brake line that's not meant to expand at all. And also along these brake lines, you'll see stuff like this or this. And those are sensors that tap into those brake lines.
That's Kieran revving.
Kieran, shut up! We're filming a video! So those are just measuring the brake pressure for each brake line. So one of the things that's kind of nice about that is that because the way we get our brake bias between the front and rear is that we're just manipulating the pressure in the lines. The brakes themselves are identical. But for next year's car, we're thinking of actually shrinking the rear brakes to make them less effective. But what that means is that we won't have like a completely accurate gauge of how much brake bias is going in the front and back. It's not really important. It's just like a gut check to confirm what you're already doing. For the most part, the way we adjust our brake bias is you have somebody go and stomp on the brakes, and you're just looking for which tires lock up first. And then you adjust it forward, backwards, regardless. Another thing that we're thinking about adding this year is a dash-mounted brake bias adjuster. So that's just a cable that attaches onto this balance bar, which we talked about earlier, and it'll just be a little knob that you can adjust on the dash, and it rotates the balance bar and moves the fulcrum back and forth. And then those brake lines come back to the actual brakes, which you can see in here. I don't know if you want to come around, but the brakes are mounted onto the uprights, and then the brake rotors are mounted to the wheel. So the brake calipers just have one pot inside them. Pot is like the piston that the brake fluid is actually pushing against, and then the other side is just a brake. So there's a single pot, and that's compressing brake rotors. One fun fact is that we started out with 4 brake rotors last year and broke all of them. Because at any point, we actually had all 4 wheels fall off the car. Not at the same time, but it did happen to all 4 wheels. That's the other thing that kind of saved us, is a lot of times it's nice to make parts backwards compatible. So when we broke one of our brake rotors, it was really nice to just go to Mark II and steal the brake rotors off that because they fit right on. It's nice not to update their attachment points if you don't have to. So in the future, especially with the dawn of the EV car, which is happening next year, we're also thinking of moving to smaller tires. Now, smaller tires can be better, but they're harder to make them better. Like, they have more high-end potential, but they're a lot more challenging to design around. Your packaging is harder, and also they just have a smaller contact patch, so less smaller rubber on the road, exactly. So your whole car has to be a lot, and your car has to be a lot lighter too. We're talking like 450 pounds. For this car, it absolutely. But yeah, that's something that we're thinking of going to eventually. It is like a significant investment because you have to buy all new rims, a whole 2 more sets of tires. That brings up another good point though, where a lot of these systems are dictated by the rules. I've read through a lot of the rules, but I still don't know all of them off by heart. So it's just something like when you start a project, you'll read the project regarding your rules, and then as you learn more and more, you'll learn more of the rules that you have to comply with. Yeah, I don't tell anyone to read the rule book because no one does that. But like read all the rules that pertain to your system. The way you do that is just like Control F and search for keywords that apply, like brakes or something, and then just like read all the rules that apply to